Hello, calculus students. Today we're going to explore a fundamental concept called continuity. Intuitively, a function is continuous if you can draw its graph without lifting your pencil from the paper. This curve, for example, is continuous everywhere. There are no breaks, jumps, or holes. For a function to be truly continuous at a specific point, say x equals c, it must meet three specific conditions. First, the function must be defined at c. This means that f of c must have an actual value. You can't have division by 0 or other undefined results. Second, the limit of the function as x approaches c must exist. This means the function must approach the same value from both the left and the right side. And third, the value of the limit must be equal to the value of the function at that point. This final condition ties everything together. If any one of these conditions fails, the function is discontinuous at that point. Let's see what happens when a condition fails. First up is a removable discontinuity, which looks like a hole in the graph. Consider the function f of x equals x squared minus 4 all over x minus 2. At x equals 2, there is a hole in the graph. Let's test our three conditions at the point c equals 2. First, is f of 2 defined? If we plug in 2, we get 2 squared minus 4 over 2 minus 2, which is 0 over 0. This is undefined. Since the very first condition fails, we know the function is discontinuous. But let's check the limit. As x approaches 2 from either side, the graph gets closer and closer to a y value of 4. So, the limit exists and is equal to 4. This is called a removable discontinuity because the limit exists. We could remove the break by defining f of 2 to be 4. Next, let's look at a jump discontinuity. This occurs when a function jumps from one value to another. Consider this piecewise function. Notice how the graph jumps at x equals 2. First, is the function defined at 2? Yes, according to the definition, when x equals 2, we use the second piece. So f of 2 equals 2 plus 1, which is 3. Now, does the limit exist? For this, the left-hand and right-hand limits must be equal. As x approaches 2 from the left, the function approaches 2. But as x approaches 2 from the right, the function approaches 3. Since the left and right limits are not equal, the overall limit does not exist. Condition 2 fails, so we have a jump discontinuity. Finally, we have infinite discontinuities. These occur where a function has a vertical asymptote. Consider f of x equals 1 over x minus 1. This function has a vertical asymptote at x equals 1. First, is f of 1 defined? No, plugging in 1 results in division by 0. Condition 1 fails. Second, does the limit exist? As x approaches 1, the function goes to positive or negative infinity, not a specific finite number. Therefore, the limit does not exist. This is an infinite discontinuity. So why is continuity so important in calculus? Continuous functions are predictable. They don't have sudden jumps, holes, or fly off to infinity. This predictability is crucial when we study derivatives, which measure rates of change. You cannot find a meaningful rate of change at a point where there is a break. Continuity ensures a function is well behaved enough for us to analyze with the powerful tools of calculus. Thanks for watching.